All right, great. Thanks for the introduction, and welcome everyone. Glad so many of you could make it to our talk today. Before we get started, who are we? We are my colleague Yovli and I. We are both ML engineers at Schwarz IT, and Schwarz IT is a daughter company of the greater Schwarz group. And so are both retail giants, Lidl and Kaufland. Today, we will take a deep dive into the forecasting we do at Lidl. We'll go into the reasons why we are doing forecasting in the first place, and most importantly, and likely the reason why you're here today, is how we are doing it. So let's get started, and we'll first start with a small motivation. Imagine yourself as a store manager at Lidl, and it's time for you to reorder bananas for the next week. And you ask yourself, how much should you order? Ordering too little, and you end up with unhappy customers, you will lose out on sales, and your customers might even go to the competition instead. Ordering too much, on the other hand, you will end up throwing out bananas that went bad on the shelf. This, of course, also means money down the drain. And such ordering has been a manual process for quite a long time. However, as we all know, manual processes are slow, they are expensive, and also error-prone. So what we instead want to do is, we want to come to this decision in a more data-driven way. We want to use our historic sales and get a good estimate of our future demand. Then we can make an informed decision on how much we should order. This not only improves customer satisfaction, reduces waste, but in the end, it also increases our profits. To understand where we can actually leverage these forecasts, let's take a look at a crudely simplified supply chain at Lidl. On the far right-hand side, you have our customers. Here, we want to ensure that our goods are always available. However, the customers are also the biggest source of uncertainty. Customer behavior at its core is stochastic. Just think about how different your shopping cart might look from one day to the other, or how a promotion might affect your shopping. So all the previous steps have to account accordingly. So the store has to stock enough goods, which can only be delivered from the warehouse. And this has to then, in the first place, been ordered from the supplier. And actually, in all of these use cases and positions in the supply chain, we can make use of forecasts. So on the far left-hand side, at the supplier, we can use our forecasts to aid in the ordering decision, to aid in optimizing logistic processes, and this requires quite long-term forecasts with a rough granularity. On the other hand, closer to the customer, we can actually also optimize processes in our stores. One such example is our bake-off stations. Here we optimize how much and what to bake off to ensure that our goods are always fresh and available. This requires quite short-term horizons with a high granularity. Lastly, in the middle is one of our biggest use cases, the so-called automatic dispositions. Here, forecasts are used to automate the ordering and also the disposition from the goods to the warehouse and stores respectively. Both of those use cases use daily forecasts, so a forecast is generated for each and every single day. And the warehouse requires roughly 4 weeks in advance, where the store only requires a single week. Through the remainder of this talk, we will focus on this warehouse level use case. So all the plots you will see are on the warehouse level. However, everything we say basically holds for the other use cases as well, with just minor tweaks and adjustments to account for the differences. Now, this was all a bit theoretically. Let's now take a look at a more concrete example. Here you can see the normalized sales for a single item in a warehouse. These are the sales for banana throughout the year 2024 in a warehouse in Austria. And our time series that we are faced with have a few certain properties. So first of all, it's quite apparent that we have a super regular weekly pattern. This is what we also refer to as weekly seasonality. On top, you can see that we also have more long-term patterns, so yearly patterns, where you see that we sell less bananas in the summer, likely because maybe strawberries are also available, while we sell a lot in the winter. This would also repeat throughout several years. Besides these regularities, we also see some irregularities. So here you can see that we, for example, have a big spike in our sales, which was caused by a promotion. Our modeling approach thus has to be able to also account for such irregularities. And lastly, we are faced with a lot of different time series. So the time series for each store, for each warehouse, and especially between each item varies quite a bit. So our modeling approach has to be quite flexible in that regard as well. Now, analyzing time series is nice and well, but how can we actually model a time series and how can we predict? And there's quite a few options to do so. And it has quite a long and rich history. Early on, time series forecasting has been dominated by more traditional statistical approaches, such as order regression or even moving averages. The focus of research has shifted. More recently, their focus is way more on deep learning, and everything from simple MLPs over LSTMs all the way to transform models has been explored. However, there's one approach that has been proven to be super effective in industry, and this is treating this forecasting problem as a tabular regression. How we can do this? You just take each data point in time series, and it becomes a single row in your table. What advantages does it yield? You can rely on any traditional tabular method. And these are super well explored and well established. Additionally, you can actually easily extend your data set with additional features, such as engineering features based on the time or adding external information about promotions, for example. Now let's make it more concrete regarding our modeling strategy. And here I want to talk about two concepts, which is training granularity and training level. Training granularity basically refers to how granular or how small are the predictions our model makes, and thus what do we train on. While training level is referring to the scope that one model has to cover. So how much data do we pool for one model? For the training granularity, you can see we make predictions on the item, store, day level. And this is almost the lowest granularity in all the dimensions. This has multiple reasons. The first being our downstream processes require these low granularities, so it makes sense for us to model on these as well. But we also can make use of these lower level forecasts, aggregate them up, and get really high accuracy in even higher aggregation levels while being in line with the low aggregation level. For training level, we train a single model per item warehouse combination. So a single model only is responsible for predicting the forecasts or the demand for a single item. But it does so for order stores in a warehouse. This yields the advantage that we do not, or we can make sure that our model does not explain the demand or predict the demand based on the history of a different item, while still having cross-learning between stores. So a newly introduced store could still have good predictions right from the get-go. Now, I've already introduced modeling time series forecasting as a tabular regression, but there's still a lot of options. We actually choose to use a tree-based gradient boosting method, and I think most of you might be familiar with LightGBM. And there are a lot of reasons why to use LightGBM, but I will go into the four most important ones for us. The first one is, of course, its cost. We train hundreds of thousands of models based on our training level regularly, so the training, but also the predictions, has to be cheap and fast. And this, of course, whilst offering good prediction quality. Along those lines, with scalability, we can't oversee all our models. We can't oversee all of the predictions we do. So we have to make sure that our model training and predictions are quite stable. This is also the case for LightGBM. The next point goes more towards the implementation. So we all know LightGBM is well established, and LightGBM is open source, which I think is always great, and it's actively maintained. So we know that support can be guaranteed. Lastly, and I think that's a super important point to drive home here, tree-based methods are more easily explainable. So first of all, that means that if we see that a model is off, we can look at the historic sales of an item, and we understand why the model predicts as it does, and how we can avoid it in future, and how we can improve our approach. But also, we can explain to the stakeholders, to the business, how the model works. This allows them to understand the capabilities, but also the limitations of our models. And this just saves a lot of headache. Now, no model is complete without its feature set, and our features can be categorized into roughly 5 groups. And each feature group actually contains a collection of features, continuous, discrete, and also categorical ones. The first one are calendar features. I've talked about earlier about some regularities, patterns that we see. These calendar features are engineered to best represent these seasonalities so the model can correctly understand those. The second group is also called calendar features. However, these are now related to holidays. Here it's super important to understand that a model should not learn the effect of holiday based on the data alone. This can especially be hurtful if you think about moving holidays, such as Easter, because then the model could overfit and overpredict even though there is no holiday in that specific year. Next up, you've seen how big of an impact promotions have. They cause huge spikes in sales and demand. So we have a dedicated feature groups to best model the effect of promotions. we train our models on warehouse level. So a single model has to predict for multiple different stores. Stores are quite different. Just think about how a store at the beach might behave compared to a store in a mountain resort. Thus, we have some store-specific features to better differentiate those. Lastly, this is quite common practice when treating time series forecasting as a tabular regression, are lag features. Lag features are just incorporating information of preceding days. For example, one could imagine the sales 2 weeks ago as a feature. This way, the model has an easier time to recognize certain sales pattern and even helps in differentiating different stores. With that already sums up our quite basic base modeling approach. And I'll hand over to my colleague Yovli, who will show you how well does such a basic approach work, how to increment it, where are its limitations, and finally, how we end up at our forecasting engine.
Thanks a lot, Moreno. Let's now apply everything that we've learned so far on our banana item. So for that, we go back to the sales of the banana item for the year 2024. And additionally, we add the sales, additionally to the sales, we add the predictions in gray. What you can observe at first glance is that generally, the predictions of the model actually match relatively well the sales, especially through seasonality patterns that Moreno mentioned earlier, so the weekly pattern and the yearly pattern, the fact that for the banana, the sales are generally lower during the summer and higher in the winter, are very well captured. There are, though, 2 time periods, especially in the time series, where the model simply fails to capture correctly the pattern of the sales. And not completely coincidentally, these periods are full of holidays. This is the reason why in the second part of our talk, we will show and explain to you why we evolved from a relatively basic modeling approach to a much more complex one, especially using the example of holiday. Now, if we zoom in into one of these periods to understand a bit more why do the prediction fail to capture the sales so well, we first start by displaying the holiday events. Here you can see that there are links to 0 sales. That means on these days, likely all of the stores for the warehouse were actually closed. And you can imagine thinking about your own behavior that what would happen is that simply the sales would get redistributed to the days nearby. What we in turn observe is that generally the predictions of the model in gray, they completely fail to achieve the level of the sales. And even worse than that, if you actually compare the predictions to the week following the holiday events and preceding the holiday events, actually the predictions are not so much higher, which is definitely contrary to our expectations. Lastly, not completely coincidentally as well, we see that after this holiday periods, we have one day with very low sales that cannot really be explained by a low demand because it is just simply too low. And likely here we can make the assumption that because of this systematic underestimation that happened around the holidays, then simply the supply chain was overwhelmed and they ended up not delivering enough goods to the store. So far, we only talked about the banana item. You can imagine that the way the model struggles with holidays is actually much more generic. And what we'll do next is try to understand why the model struggles so much with holidays. For that, let's try to explain what are holidays about in general. So each country has a certain set of holidays, like Easter, like Christmas. Generally, they have about 10 holidays. If you're living in Bavaria, potentially you have up to 13 holidays, but generally it is around 10. If you now consider that we train on about half a decade our models, then we end up by having about 100 holiday events that any model could use to actually understand the holiday pattern. This is quite limited, and thus the holidays events are quite sparse. This would on its own not be a problem if at the same time holidays would not be very diverse. So no holiday is actually exactly similar as the holiday previously. We've identified up to 10 factors that influence heavily the effect of holidays. Among these 10, 2 are quite important. So first, the day of the holiday. Is it Easter? Is it Christmas? And secondly, also the day on which the holiday falls. So you can imagine if a holiday falls on a Saturday, then the sales will get much more distributed to the days nearby than if it actually falls on a Tuesday, where the sales are relatively lower generally. In that case, taking these 2 factors into account, we actually see that the combination, so the cardinality of the combination set for these 2 factors already attained about the amount of samples that we have in our training set. That means that generally all machine learning models would potentially, even using only these 2 features, already struggle to capture properly the effect of these 2 features. Now, additionally to this complexity in modeling holidays in general, we have also some restrictions that are forced onto us by our modeling approach. So again, we train one model per item warehouse. What this means is that generally the information of the donut, as an example, as an item, cannot be used to predict the holiday effect of the item croissant. The direct implication of it is that items with low history, so newly introduced items have potentially a couple of months of history, they either lack the data for predicting holiday properly, or they will even not predict holidays as well. In the same direction, items with strong shelf shift, and that is rather due to the nature of tree algorithm, will also fail to do so. Lastly, our time series on the store or warehouse level are quite noisy, and the model may struggle to actually recognize that the high sales spike, as an example, is due to holiday effects or is simply due to some noise. We made back then these observations and decided to improve on them. And what we first did is we introduced two specific features to our model. First, we introduced feature contribution. Feature contribution, what is it? It is a specific feature or hyperparameter of the LightGPM that helps us to weight certain features higher than other ones. This is generally also a concept that could be reused in much more modeling approach. Why does it make sense? Is that potentially some items just simply lack the data, and some expert knowledge could actually help the model make a better, explain better the sales data. The implication for our modeling approach is that basically by using feature contribution, we use it on holiday features, and in turn, this leads the model to generally predict holidays using previously seen holidays that are relatively similar to the model. This is, again, especially relevant for items with a shorter history, because for them, the model will just simply lack the ability of explaining data properly. Secondly, we had also sample weighting, which is a much more common technique in machine learning. There, what this is about is that simply samples that are underrepresented get multiplied so that the model decides to explain them in more details. Let's now go back to our previous example of the banana item, and we will add on top of the sales and the predictions of a LightGPM baseline model, we will add the predictions of this newly trained model, the LightGPM tuned, that contains the feature contribution and the sample weighting features. What you can observe at first glance is that while it is a step in the right direction, so it seems like the forecast actually increased, the pattern is still not properly captured, and also the model still fails quite heavily at predicting the holiday. So we considered that this was also unsatisfactory in general. At this point, we decided to completely change our modeling approach and go with something that is much more complex. We introduced the so-called holiday uplift model. What is the holiday uplift model? It's a model that makes the assumption that generally the effect of the holiday is multiplicative, and that tries to capture it. We train a single model for the entire world also to not be subjected to the 4 limitations that we presented to you earlier. And our hope is that in that case, this holiday uplift model can actually come up with better uplift or impact of the holiday forecast than what our base LightGPM model would do. To be a bit more concrete here and to make sure that you have understood what the model is about, as an example, our model would be capable of predicting that on the 23rd of December, so one day before Christmas, there is, in comparison to a reference week, potentially 30% uplift. Now, the question still remains, even if we have some relatively accurate predictions of the uplift due to a holiday, how do we use them to improve the demand predictions of our model? For that, we rely on the so-called decompose-recompose approach. What happens is that we decompose the time series that goes into our base LightGPM model, meaning that the cells around holiday get divided very concretely by the uplift factors. So the base LightGPM model is not expected anymore to actually predict much of the holiday effects. And then the forecasts are generated, and the holiday effect is re-added by multiplying the uplift factor by the predictions of the base model. You can guess the next step. We will again go back to our prediction and of the different models in the cells, and this time add on top the predictions for the banana item of this new model. Here you can see that actually for the banana item, the improvement is quite significant in that case, and that the predictions relatively well match the cells. There is still some gap, though, that can be either explained by either just the lack of data or some randomness potentially for the events, or even some potential for improvements in the approach. So far, we've only presented to you one item, the banana item, so that we can convey as much as possible the intuition behind it. But this is in no case a mathematical proof that these models are better. That's why to finish the evaluation in our talk, let's extend it to the complete item scope for Austria for the entire year 2024. And here we're only evaluating the days in the proximity of a holiday. In that case, it's not possible anymore to just simply compare time series of sales and forecasts to get an intuition what model performs better. We need to rely on metrics. In that case, we decided, or we selected, a relatively common metric in the context of time series, which is the mean absolute percentage error that we compute on the aggregated sales of all the items and all the stores. We also compare the value of each model to the value of the LightGBM baseline model. Here, for those of you that are maybe not too familiar with these metrics or with time series in general, an intuition behind it, or what it measures generally, this metric would be how well does the model is able to capture the holiday effect on the highest level. Now, if we compare our model, we see that the first iteration that we made actually already represent quite some improvements, so 6% improvement for this metric. And the second model that we tested really was a complete game changer, and then going from 100% then to 75% for this metric was a gigantic deal for us and definitely justified implementing it. Let's sum up what we did so far. First, we started by presenting to you our base LightGBM model, which represents the backbone of all our modeling approach and is generally a very effective way of generating forecasts that are quite reasonable and that are able to capture most of the effects that one can find in time series properly. Afterwards, we identified together that this model lacked the ability of properly predicting holiday and showed that in that case, making use of the holiday uplift model actually improved the performance of the forecast quite significantly. And you can imagine that holiday effects are also not the only ones where potentially the base model struggle and where some higher level modelization can actually improve the performance. So here also, I imagine maybe not as a surprise, in our whole modeling pipeline, we not only have the holiday uplift model, we have different so-called modeling capabilities that can be seen as model specialists that are targeted to predicting certain behaviors much better than the base LightGBM model. Developing all these models is also quite some effort, so they are generally built around the same templates, and very importantly, they actually build through a unified feature engineering to make their development faster. Now, to the last part, once we have all these capabilities, and you already saw it with the example of the holiday, we need to combine them, to piece them together to create the highest value forecast. And these forecasts, they will then flow into multiple use cases that may have certain expectations around the forecast. That is why we also have a post-processing step that is specific to each use case. Maybe to give you here a concrete example, in the supply chain, it may be that the suppliers require actually some upward trends on the forecast to reduce the risk of having underestimation. And currently, we're only serving a couple of use cases in the supply chain, but our long-term plan or vision is that actually this forecasting engine is able to provide forecasts to the whole Schwarz group and there improve the business process there wherever it is necessary. With these final words, we're arriving to the end of our talk and would happily answer all the questions you may have related to this topic.
Yeah, so thank you a lot for your talk. We have a lot of questions. We will not be able to answer them all, but maybe you can come to the front after the talk and ask the speakers directly. So the first question is, how often do you have to retrain your model to adjust for data drift caused by current trends?
So our models are retrained weekly. So each week we do retraining for all the models available.
Mm-hmm. And how do you handle new products?
So new products, the hope is that they can already be covered already by the existing forecasting engine. If they have some specific requirements related to the forecast, as an example, then maybe they have, as an example, a different item set. Maybe we're not talking about the supply chain directly for the Lidl stores, but maybe we're talking about the online shop, as an example, that we need to adapt some components of our engine to actually provide this forecast for a much bigger scope.
Mm-hmm. And also, do you also have a... Can store managers also override the decision of the model if they think they know better?
So not store managers directly, because you can imagine at Lidl, Lidl is quite a giant, and we produce then millions of forecasts every day, so they cannot check every forecast, and every store manager cannot do so. But what happens is that on the warehouse, they are able to check through some monitoring tools, generally the global quality of the forecast, and accordingly potentially set some high-level trends on the forecast. But otherwise, everything is automated.
Have you also considered using some monetary metrics to optimize, for example, incorporating financial effect of over or understock in your predictions?
So we would like to do so. The issue is that this will require also potentially to conduct some A/B tests if we want to do that properly. And at the end, the stock data is also not entirely reliable. So generally, we just shied away, and it is also quite hard to access at Lidl. So.
Another question was, how do you avoid unwanted feedback loops? For example, if you have too little sales forecasted, you don't stock enough products, you have lower sales because of that, and then you even have lower sales forecasted.
Yeah, usually I would say we do not have like an automated way, but we get direct feedback from the countries. They can tell us if our forecasts are so off that we actually see these negative effects, but I think we rarely got that feedback, so far we do not see the need to do so.
And also maybe to add here, what can be said is that generally the out-of-stock situations are relatively limited. So it would be rare if an item would have, as an example, 80% of its data set polluted with out-of-stock situation that would not really represent then the demand per se.
And then we have time for one last question. What were the downsides of training one global model, so including all categories and stores, compared to training many local models?
That's a good question, because that would be the different route. So what we now did is we kind of exported one capability to the global model, but of course we could have also said that we do it for the whole model. Then of course we get a whole new set of challenges. We have items with a lot of history, some with higher business impact, some with lower business impact, and that of course requires a lot of testing, a lot of discussion with the business itself, and might even have some challenges that could not be solved that easily. As our base forecasts are quite stable and we are quite happy with how they work, the best course of action for us was to just move this one capability outwards. On top of that, of course, it also means a big shift in paradigm, even bigger than what we've done now, as we have to change our whole infrastructure or entire code. This is also, of course, a consideration with costs.
Thank you. Unfortunately, we don't have time to ask more questions. We have many, many questions. So you don't have a booth here, as I saw correctly, but you will be around in the next few days. So I think you can ask them directly if you have more questions.
Yeah.
For now, I want to thank you. And yeah, thank you for the talk.
Thanks a lot.
Thanks.